Eat some meatballs. If you've never purchased anything from IKEA, this is how it works. You go through the showroom, and you see all of these neat furniture pieces and complete ensembles. When you find something you like, you write down what it is, eat some meatballs. Then you go to the warehouse, and you pick up a whole bunch of seemingly unrelated pieces from different points in the warehouse. When you get your goods home, you take out the instructions, and you use what seems like pretend play tools, and follow a bunch of steps that may or may not make sense, and when you're complete, you have a passable representation of what you saw in the showroom. It's like magic. This same type of principle can be applied to electromagnetics when it comes to using a Smith chart to analyze transmission lines. A Smith chart is just a graphical tool that we can use to look at transmission lines. You follow a bunch of steps which at surface value appear to be nonsense, but when you're done you have a complete description of transmission line parameters. Another magic trick. Oh, I'm sorry, I meant an illusion. Before we look at an example, let's take a good look at the Smith chart. Basically, there's a complex grid with the horizontal axis being real and the rim of the circle being imaginary values. Then there are two rings around the outside. The inner ring is either angle of reflection or angle of transmission, ranging between plus and minus 180 degrees, and the outer ring is wavelengths either towards generator or towards load, ranging from 0 lambda to 0.5 lambda, repeating every 0.5 lambda. Now we're going to look at an example where I want to use a Smith chart to get a whole bunch of transmission line parameters. I'm given only the characteristic impedance of the line and the load impedance. Since we have the load, we'll want to be looking at the reflection back towards the generator. The first thing I'll do is I'll find the normalized load impedance by dividing the load impedance by the characteristic impedance to get 0.5 minus J0.25. I'll then go to my Smith chart and mark that point. On the horizontal axis I go over to 0.5 and then I'm going to go down to negative 0.25. In part A, I want the voltage reflection coefficient, gamma. I find this by first drawing a circle on the Smith chart centered on a real value 1 and passing through my point. It's really difficult to draw this accurately on an iPad, so please forgive a little sloppiness. Once I have my circle, I'll draw a straight line from the center of the chart through my point, all the way to the edge of the chart. Then I'll measure the distance to my drawn circle. In this case it's 2.7 centimeters. I'll also get the distance to the inner ring of my chart, which is 7.5 centimeters here in the original form. The last thing I need to find gamma is the angle of reflection, which I can read from the chart as negative 144 degrees. Okay, to get the magnitude of gamma, I take the distance to my drawn circle divided by the distance to my inner ring and get 0.36. I already found the angle of reflection is negative 144 degrees, so putting these things together I get gamma. In part B, I'll find the voltage standing wave ratio S. I find this by taking 1 plus the magnitude of gamma divided by 1 minus the magnitude of gamma, yielding 2.125. I could also find this on the chart. It's the location where my circle crosses the real axis to the right of 1. It's not that close on my drawing thanks to the sloppy iPad realization. To understand part C, finding the location of the voltage max and min, we need to understand that reflection in a transmission line results in a standing wave, which has maxima and minima. We want the closest max and the closest min to the load. It's also valuable to look at the standing wave on a short-circuited line. In this case, it's clear that the max is located at lambda over 4 and the min is located at lambda over 2. So to apply this to part C, I first look at where the load is located and find that it is at 0.45 lambda. To find the first voltage max, I take the short-circuited max, 0.25 lambda, and subtract my load location. I get negative 0.2 lambda, but it's nonsense to have negative distance. So, knowing that the chart repeats every 0.5 lambda, I see that this is equal to 0.3 lambda. To find the first voltage min, I take the short-circuited min as 0.5 lambda and subtract my load location to get 0.05 lambda. In part D, I need to travel from the load back to the generator to find the input impedance. I go to my Smith chart and I'll travel 2.2 lambda in wavelengths towards the generator. Since the chart repeats every 0.5 lambda, I can go around 4 times and get back to my original location at 2 lambda towards the generator. Then I go the remaining 0.2 lambda and end up at 0.15 lambda. I then draw a line through 0.15 lambda wavelengths towards generator and the center of the chart. Where my line intersects my drawn circle is the value of the normalized input impedance, approximately 0.95 plus J0.75. To get the input impedance, I multiply the normalized value by the characteristic impedance 200 to get 190 plus J150 ohms. Finally, to get the input admittance, I just need to travel 180 degrees, or 0.25 lambda from the input impedance. With a straight edge, I can just continue my input impedance line the rest of the way through the circle, and see where that intersects with my drawn circle. It intersects at approximately 0.65 minus j 0.5, again having a little grace for the poor drawing on the iPad. This value is my normalized input admittance, and to get the actual value, I need to divide by the characteristic impedance, and I'll get 0.0033 minus j 0.0025 mhos, or Siemens. Hopefully this video gets you a good push start for using Smith charts. Thanks for watching. Best of luck.